Hello everyone. Today we are going to cover chapter 6.5 Space Trusses. So far we learned how to find the magnitude of the force in truss members. Also, we can identify whether the force is in tension or in compression. Uh, Today's lecture is it's a very similar thing, but in 3D space. So this is we call the space truss. So members are joined together to form a stable 3D structures. So we call this is a tetrahedron, the simplest form of a space truss. So here you can see that we have how many members here? 1, 2, 3, 4, 5, and 6. If we want to extend this truss, then we can add another 3 members. Also, we can add another 3 members here. So we can, add 3 members, and we can continue to expand this simple truss. So this is a very economically it's not expensive. This is very cheap and also provide a lot of support to hold the weight. So that's the reason why the many construction sites they use this space truss for the bridges or for the electrical transmission tower or roof. Okay. And one thing that typically these space truss are connected with a ball and socket joint. So ball and socket joint is there are 3 support reactions, which is translational restrictions, x, y, z axis directions, but rotation wise there is no restriction at the joint. So assumption for space truss, all the members are two force members. So that means they are support. They have a same magnitude at the end point, but the opposite directions. So think about the tension. So tension is a pulling force, right? So it's pulling the force from the joint to another joint. Okay, and also the other side there is a pulling force, so it pulled to the another side. The second one is all the external loadings is applied at the joint. Okay, so joint has a lot of load. Okay, they are all connected with the ball and the socket. If the structure has a weight, obviously in our problems we assume that there is no weight, but there is a weight in rare cases. So in that case, we can apply the half of the weight at each side of the joint. Okay, so half of the magnitude applied at each end of the member. Oh, like I said, this ball and socket has 3 restrictions. That is x-axis directional restriction, y-axis and z-axis. There is translational restrictions for the ball and socket, but the rotation wise it's free. So we can use this equilibrium equation to solve the problems. So for example, if we can use method of joint and the method of section, that's what we learned last class. Method of joint is you can see that at the joint, since they are all connected with the ball and the socket, all the horizontal force, horizontal and the vertical translational movement, the force should be equal to 0. Method of sections. Method of section, we can use this translational restriction. Also, there is no rotations since the space truss is a very stable object, so there is no rotations. Okay, so all the moment, if you add up all the moment for any directional rotation should be equal to 0. Okay, there is no rotations. Okay, now let's solve the last problem of chapter 6. This is a 3D space truss. But this looks very complicated, but actually it's not that difficult to solve this problem. The question is, determine the forces acting in the members of space truss. So we have how many members here? We have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, we have 9 members here. But let me show you how to solve this problem. Oh, by the way, we have a 3-dimensional coordinate system. You can see that this direction is y-axis and the x-axis here and z-axis. That means the joint C is origin. Origin is 0, 0, 0. And E, we can see that for the x-axis it's 2, y-axis 2, and the z direction is 0. For the A, we can say 0, 0, 2. This is the location of the point A and point E. And if you look at the point A, we have a support. No, not support. It's a external force, which is a kind of a pulling force toward the negative y-axis directions, which is good. So we can solve this problem easily because we have an external force over there, and we have 3 unknown members. That is number 1, AC, number 2, AE, number 3, AB. So we have 3 unknown force members are associated at the joint A, as well as we have 1 known external force. So that means we can use a 3 equation, 3 unknowns. That means this is solvable. So let's solve the problem starting with the joint A. Okay, let me take off the keyboard. Let me draw the diagram. So we can show the dimensions, and then this is joint A, B, this is E, D, and C. So all the joints are connected with ball and socket. There is external forces. Let's draw another color for the external forces. For the A, we have negative y direction, that is 4 kilonewton. Another force which is downward direction, this is 2 kilonewton. So we don't know the 3 forces. Let's assume they are all in tension. Okay, this is our assumptions. So tension means it's pulling forces from the joint A. So the direction of three unknown forces are pulling from the joint A. Okay, so this one I'll say this is force AC. This one force AE. This one is a force AB. Okay. Luckily, force AC is on the z directional axis, so there is no x and y component. Force AB, this is directly above the y-axis direction, so there is no x and z component. How about the FAE? The AE has a diagonal direction, so it has all the x, y, z component. So, but we have a dimensions here, 2 meter, 2 meter, and 2 meter. Well, what we can do is we can find the vector from the A toward the E, and then we can calculate the unit vector and multiply the magnitude of the force that is the force vector, right? So we can express this force vector AE with Cartesian vector notations. The first one, we can calculate the position vector. The position E from the origin is here, which is O here. Origin, this is the 2, 2, 0, and A is 0, 0, 2. So let's find the position vector toward A toward E. So that means E minus A, right? So that is 2, 2, minus 2. We can find the unit vector AE. Basically, we can just divide by the magnitude of this position vector. You can see that the magnitude should be square root 8 to square root 8 minus 2 square root 8. This is the position vector, and the force vector AE is, we don't know the force AE. That's what we're going to figure out, and then multiply this unit vector. Do you remember the unit vector, guys? Okay, good job. Alright, let's solve the problem by applying the equilibrium equation. Like I said, since this entire truss is in equilibrium, we can apply equilibrium of equations. Sigma fx equals 0, sigma fy equals 0, sigma fz equals 0. So about joint A, I think for the x-axis force there is only one force is associated, which is this one, FAE times 2 over square root 8. So sigma fx should be equal to 0. Only this force, FAE square root 2, these forces are associated with this x-axis x directional forces. This is equal to 0, so that means FAE is 0. FAE is a 0 force member. How about the y-axis, Fy equal to 0? For the y-axis direction, we have a minus 4 kilonewton about joint A, and we have a AB, force AB. Also, we have a plus FAE, which is a 0 force. But let me write down for the full equation. This one equal to 0. So since FAE is 0, that means FAB is equal to 4 kilonewton. And the direction is right? because there is no negative sign here. So our assumption was correct, which means this one is in tension. Member AB is in tension. The last one is sigma fz equals 0. Let's see, for the z directional forces, how many forces? Okay, we have one negative forces, m minus fac, because this is a downward direction. I put the negative sign. Another one is minus fae, 2 over square root 8. Okay, so this one should be equal to 0. Since AE is 0, then AC should be equal to 0. So force AC should be equal to 0. So AC, this one is 0. AE, this one is 0. And AB is 4 kilonewton, which is a tension. Okay, now we find all the unknown forces that are associated with the joint A. Now we can move on to the point B. Okay, point B. If you look at the point B, there is external force which is 2 kilonewton here. Okay, so 2 kilonewton, and there is a tension. That means the left direction, because this is a pulling force. Okay, it's in tension, pulling from the point B. Okay, so the left hand direction, and there is three another unknown forces, 1, 2, and 3. So since we have a 3 equation, 3 unknown, which means this is solvable. Okay, so I'm not gonna solve all the members forces. So I just want to give you some idea how to solve these problems. So once we figure out the unknown forces from the point A, then we can move on to another point and then solve the problem. Next, move to the point D and E and C. That's how we can solve the problems. Okay. So you can find the answer in the next slide. Okay, so that's today's class, which is relatively short. Here is an announcement for the midterm exam 2. Next Tuesday, like I announced, we have a midterm exam 2 at 11 a.m. on the blackboard. We will cover 4 chapters. Chapter 4, three chapters. Chapter 4, Chapter 5, and Chapter 6. We just finished the Chapter 6, so next week we will start Chapter 8. We will skip the Chapter 7, okay? This is open book exam, so you can check my lecture slide. I'm thinking some questions we didn't solve the problems during the class. I think there should be 1 or 2 new questions, okay? So please practice many times with the existing problems. There will be a slight variation, but if you know how to solve the problems, then you have no issues to solve the problem. You will need an engineering calculator. This is 20% of your final score. As usual, submit your problem solving process through the blackboard so that you can get a partial credit as well as extra credit. Thanks for watching this short video. Have a great day.